Now the total pressure is 9.5 atm. And we ask you, how does the partial pressure of oxygen in the diving gas can compare to the partial pressure in normal air? Well, we can do a calculation for partial pressure here. Okay, so in this particular case, we have percentage by volume. Okay, so the partial pressure for oxygen gas in this can, PO2, equals to the percentage of air, which is a percent of oxygen, 2%, 0.02, times 9.5 atm. That will give you 0.19 atm. The question is asking you, how does this compare to the partial pressure of oxygen at the sea level? Well, at the sea level, they're comparable. 0.19, 0.21, slightly lower. Now, if you have the regular air compressed into that container, when you carry that container and you go scuba diving, it will be 0.21 times this number. It's going to be 2.1, somewhere around 2 atm. That's the partial pressure of oxygen. You can put in too much oxygen into your body there. And too much oxygen will knock you over and it will put you to sleep. So it's harmful. Too much nitrogen will also do the same thing. And people actually discover helium, noble gas. Helium doesn't do much. So we can put 98% of helium in the gas tank, and you carry that pressurized tent and going scuba diving with only 2% of oxygen in there. You would breathe as if you were at the sea level. These two numbers are somewhat comparable. 0.19 atm versus 0.21 atm. Okay, so we could do maybe 0.2 percentage, 2.1 percentage, 2.5 percentage, well, to simulate the condition here. Now the total pressure at the sea level, you know that number fluctuates. Yesterday when we were in the lab, when we're doing when we're reading the air pressure, throughout the 3-hour lab period, that pressure is actually fluctuating up and down by a couple of millimeters of mercury there. Okay, so 0.21, 0.19, that's close enough. And that's why we have only 2% of oxygen in that gas can that you use for scuba diving there. Okay, so that's one application for the Dalton swallow partial pressure. We can figure out the partial pressure for the oxygen gas. All right, so this is something that, well, a continuation of the calculations we're introducing there. So we have 7 questions and 7 examples running in chapter in the second learning objective there. So this is number 8. Okay, and we can ask you another question there. A mixture of 50 grams of oxygen gas and 50 grams of methane put together, and the pressure is at 600 millimeter mercury. What is the partial pressure for each of the gases here? Well, the question only asks you for the partial pressure of oxygen. Okay, if you have oxygen gas, if you have methane gas, you mix them together. With a total pressure of 600 millimeter mercury, what's the partial pressure for oxygen? The next question we're going to ask you is, what's going to be the partial pressure for the methane here? Well, in this case, in order to figure out partial pressure for oxygen, and mole fraction of oxygen times 600 millimeter mercury, this is your total pressure. So we need to figure out the mole fraction. Mole fraction, by definition, is the number of moles of oxygen divided by the total number of moles of oxygen plus methane. So we have to figure out how many moles of oxygen we have, how many moles of methane we have. Well, oxygen, each mole is 32 grams, 2 oxygens in there. So 50 grams times